I'm going to be giving you an introduction to the aspirin topic. So with the aspirin topic, what was intended was it would be a big project where you'd be making aspirin, extracting it, actually not extracting it, making it from salicylic acid, changing it, recrystallizing it, extracting it from the mixtures and making it a really pure compound as possible, and doing tests to show it's pure. Now we hope to do that later on in proceedings. But another part of the project is to actually plan and do some research on aspirin, which I think Judith will talk to you about. So I'm Nick, and I'm going to be talking to you a bit about the basics of aspirin to start with, and some of the chemistry that's involved, and I'll be using various aspects of what we've got already set up. So, aspirin, okay, let's make myself a little bit smaller, there we go. Okay, so, now, on OneNote we have our booklet, so the aspirin booklet as labelled up here. Okay, so here's the aspirin booklet. And this is the introduction to it, as you can see. Okay, so we'll scroll down a bit. Okay, now what we're going to do is we're going to start to look at aspirin itself. Now, I haven't got a model of aspirin, but here on my table, let's get rid of the aspirin for the moment. Here on the table, I've got a molecule, a molecule, which is salicin. Now, salicin comes from the Latin word salix, which is from willow. Now, in a previous course, I have actually collected willow bark. Obviously, I've peeled off stuff that's sort of like dead or dying, and we've actually tried to extract the salicin and then convert it into salicylic acid or acetosalicylic acid, which is actually aspirin. Now, this is the molecule of aspirin. Now, actually, where my hand is, there would be a molecule of glucose. So it would be a link from this benzene ring via an oxygen to a glucose molecule, and that is what salicin is when it's found in willow bark. Okay, so let's hide that. Right, so if we look at the diagram, here is salicin, which is the molecule I just showed you, with the glucose on there. It's also found in some other plants as well, like meadowsweet, which is Latin and spirea, which is another plant that contains the salicin. Now, spear, S-P-I-R, is where aspirin comes from, the actual name for, or the generic, or the simpler name for it. So here is salicin, okay, and of course the reason we've looked at this is because people used to chew on willow bark or use meadowsweet to try and reduce their pain, and so obviously a lot of our drugs come from these old remedies that used to be used without any scientific background behind them. So a little bit later on in time, this man from Basel, which is in Switzerland, Professor von Nenke, actually took the salicin and changed it. So what you can see is here, okay, here we've now got carboxylic acid group on here, okay, and that's come from this bit here, okay. So this is an alcohol group. It's a primary alcohol, and so it can be quite easily oxidized. Well, it can be oxidized to a carboxylic acid. And the glucose has been cleaved, and in fact that's what's actually happening inside our body. This is what's happening inside our body. The alcohol is being oxidized, and the hydrogens and the glucose being cleaved to give us this molecule. And that was found to cause pain relief, except it had some problems. Some of the problems were that it would cause so it would cause so it would cause irritation of the lining of the mouth and the gullet. So what they did was they made sodium salicylate. So let's actually have a look at, let's get salicylic acid up first of all. So there we go. So here's my molecule here. So salicylic acid, we've oxidized this alcohol part here, so we've turned that into a carboxylic acid, okay, and we have taken glucose off and put a hydrogen on here. So here is my salicylic acid, or a more correct technical name would be 2-hydroxybenzoic acid. Okay, so benzoic acid would be that. Okay, the carboxyl group at the top here is the most important group, the most important functional group of this molecule. So that's in position number 1. So this alcohol group is in position number 2. Now we don't call it ol anymore because the alcohol group is not as important as the carboxylic acid group at the top. That's on carbon number 1 of the ring, so the alcohol is on carbon number 2, and because it's not the important group anymore, it becomes hydroxy. So this is now 2, position 1, 2, hydroxy, benzoic acid, and benzoic acid is the rest of the molecule. So there is that molecule, okay? And so what they tried to do was to improve this molecule because it caused damage to the linings of the lung. So what they did was they took the hydrogen off here and they made the sodium salt, and they esterified this part here, okay? So esterified this part here. And that's the sort of big new organic sort of reaction that we're going to be looking at a little bit later on. So to esterify it, we need to put on let's grab this one. We're going to connect another carbon to probably another carbon in there as well. So what am I doing here? I need to, there's that. Okay, and then this should be another group like that. Okay, so we've got, this is sort of an ethanoate part, okay? So this side of it has come from ethanoic acid, and this was from the hydroxybenzoate, or 2-hydroxybenzoate. This was the alcohol group. So the alcohol from this has reacted with ethanoic acid to give us this molecule here. This is sodium salicate, but once they got this compound, they found that actually it was, okay, it tasted, well, it wasn't so nice to taste, and it made you vomit, so they got rid of the sodium and put hydrogen on. And now we have actually our molecule of aspirin, okay? So I'll just hold it up so you can see it. Okay, so here's our benzene ring, the benzoate, which is that bit, because that's got the carboxylic acid there, and then it's got this bit here, which is an ester link. And the ester link is a link between two carbon atoms, which are joined by an oxygen in the middle, and one of the carbon atoms has got the carbonyl group C double bonded to oxygen here. So that's our ester link here. Okay, and on below you can see that there is a mat I put on this table which says flavour and scent, because this is all about esters, and esters are responsible for lots of different scents. For instance, banana is amyl ethanoate. Some of these have got some of the old names. I've written ethanoate where it should be. So octyl ethanoate. So this has got a chain of 8, and then it's got ethanoic acid. So this has come from octanol, okay, which is in 8 chain of 8 with an alcohol on it, and ethanoic acid, and those are joined together to make octyl ethanoate, or old style we call it octyl acetate. So wherever you see acetate, it's going to be ethanoate. So there is our molecule of aspirin. I'm going to put it up that way around, because then when I switch back to turning this camera off and put aspirin back up, or the aspirin is back up here, you can see the aspirin is this molecule here, which is what I've just made. Let's make that a little bit bigger. Ooh. There you are, so there's the aspirin there. Okay, so here is our aspirin, and that's what it's all about. So there's the aspirin over there. Let's just slide it over there. There's the aspirin. Okay, aspirin up here. Okay, so there is aspirin. Right, so I'm going to hide the aspirin for a moment, and we'll go back and talk a little bit about esters. So let's put this capture device on here. So I'm going to take aspirin out of the way. You can see I've got a lot of my different esters down below. And one of the key things about esters is they're made from alcohols and carboxylic acids. Now let's see if I've got carboxylic acid left. I can smash it apart. Okay, let's take this one apart and put this back on here. So now I've got ethanoic acid, all right? And you should be able to name that, okay? 2 carbons, F. We've got our carbonyl group and our hydroxyl group on the same carbon. Okay, so that is ethanoic acid. Now here, if I can stick, actually, where's my let's grab this one. Okay, so that's that one, and let's put this hydrogen back on here. So now, here are 2 molecules. They are both stems of 2. So this one is ethanol, and this one is the ethanoic acid. Okay. Now, under the right conditions, which is basically is going to need some acid catalyst, then one of these will attack as a nucleophilic attack to act as a nucleophile and join on to the other, and it's what we call an elimination reaction. In fact, this one's a condensation reaction because the molecule that we eliminate, the small molecule that comes off, is actually water, hence the name condensation. But it's also called esterification because I'm going to make an ester. So let's think about these molecules. Here's the alcohol, the ethanol. Okay, this oxygen here has got 2 lone pairs. Okay, hence the bent shape, the non-linear shape of this, just like as in water. Okay, so it's got 2 lone pairs. Okay, that makes it a good nucleophile. It wants to find anywhere where there's positive charge. Now, if we look at the carboxylic acid, this carbon here, okay, has got an oxygen here and an oxygen here. There's lots of electrons in this double bond, okay, but oxygen has much more electronegative than carbon, so it will pull the electrons towards it. But they're also being pulled that way. So that means that this carbon here is more electronegative, okay, more positive, slightly positive, delta positive. So there's a dipole which is pulling the electrons away from this carbon towards these 2 oxygens. Now, to get a bit more technical, we don't actually know which oxygen is which. Okay, there's what we call resonance structures, which means that this hydrogen could well be attached to this one or that one, and the bond lengths here are going to possibly be, more equal than the difference. This being a single bond, so it should be longer than the double bond here. So there's what we call resonance structures. That doesn't really affect it too much, but just to bear that in mind that there is something slightly more complex going on. But this carbon here is more positive than that oxygen and that oxygen. And it's also going to be more positive, or slightly less negative, than this one here that's on the alcohol. Okay, because this one's only got this oxygen pulling the electrons away. So this is the one that's going to be attacked. Okay, so what happens is that this nucleophile comes in and wants to attack here. Now the hydrogen on the alcohol will come off. Okay, actually I'll leave, yeah, that'll be okay. Okay, and the OH on here will come off. Okay, that means we're going to make water. So here's my water molecule, which is a good leaving group. Okay, and the molecule joins on here because this oxygen which was on the alcohol has come in and attacked here. Okay, so now I've got my ester linkage. Okay, my ester linkage. I've had esterification. We've eliminated a small molecule. Okay, it's a nucleophilic attack because of the lone pairs that were on this oxygen here. Well, it's still going to be there. And now I've got my ester link. And there's that ester link. So always look for this: oxygen, carbon, double bond oxygen. That's going to be an ester link. Okay. Now later on, you'll think about things like polyester, which is a molecule which must have 2, or each molecule. So the alcohol will be a monomer, but it would have two reactive groups on either side, i.e. a diol could work quite well with that. And with the acid, that could be a diacid, so we could have an acid group at either end of the molecule, and therefore you could imagine a large molecule being built up. And that's where polyester comes from, and that's one of the major materials we have in our clothing. So this is an ester. Now the way we would name this ester is we start from this bit, which has come from the alcohol. Okay, this bit has come from the alcohol because we know it doesn't have a double bonded oxygen on it. It's only got the one oxygen on it, which is connected to the next part of the chain. So this bit's come from the alcohol, this bit's come from the acid. So we start by giving this bit as a stem. Okay, so the stem is ethyl. Okay, so this is ethyl, and then this bit, the rest of the main part of the molecule, which has got the carboxylic acid, as it were, you can imagine that is the carboxylic acid, but without a hydrogen here, just the rest of the molecule. So this is ethyl ethanoate. Ethyl ethanoate. Now, I could take something different. So here, I ran out of white, grey ones of those. Let's make it look better. Let's have a proper grey one on there. So here I've got propanol, yeah, propan-1-ol in fact, okay, propan-1-ol. So what I could do is I could replace the ethanol with propan-1-ol, and, sorry, butan-1-ol even, because it's got 4 carbons, idiot. Right, so now I've still got an ester, but it's a different ester, because this time I've got this, which has come from my butanol. So this would be called butyl ethanoate. Butyl ethanoate. And I don't know if we've got butyl ethanoate here. Don't think we have. Okay, but there's butyl ethanoate. Okay. Now I could replace the ethanoic acid with this, which is benzoic acid. Let's put a hydrogen on there just to make it proper. So this is benzoic acid. Okay, here is the ethanoate. So I'm going to replace it by taking that off, taking this off, and now I would have butyl benzoate. Butyl benzoate. So here, this has come from the butan-1-ol. This has come from the benzoic acid. So this would be butyl benzoate. And I think that will do for now.